Okay, now in this video we will go over two more theorems related with sequences. The first one is easy. Now here it gives some methods to manipulate the limit of a sequence. Say for example, if we have two sequences, now if I take this one, if we have two sequences as let's have an is equal to n/n plus 1 and bn is equal to 1/n, and if we need to find the limit of an plus bn, what we can do is we can just use this distributive property of the limit. Okay, this from this distribution property you can see that we can across this addition we can distribute the limit. So that means the limit of this addition becomes the limit of the addition of two separate sequences, right? So the answer for this one is equal to 1 and the answer for this one is equal to 0. We calculated both these limits in the previous video. So the total answer, the total limit of this addition of this sequence will be equal to 1. Now when you say the addition of two sequences, you should be able to visualize the correct picture. Okay, now an will be equal to n/n plus 1 and bn is equal to 1/n. So now this is a separate sequence and this is a separate sequence, and then an plus bn will be a separate will be a new sequence starting from 1 and goes up to 0, goes up to infinity. So what should be the first element of this sequence? That is the element created by n equals 1. That means it should be a1 plus b1. So you have to substitute the terms accordingly and obtain the value at the first position, and the second position will be a2 plus b2, right? So there is a certain value corresponding to n equals 2 here, right? So you should calculate all those values according to the given formula and in this case it is an plus bn, and for each n we can have the value for n and we can have the value for bn, and the addition of those two values will create another sequence, and the limit says that these values will also converge to 1 when n goes to a large value. Okay, and the second theorem is known as the monotonic sequence theorem. So there it says every bounded monotonic sequence is convergent. So that means if we have a certain sequence and if it is bounded and monotonic means either it exhibits the property of increasing or it can either be decreasing, right? But not both. So now if we have a sequence, now for example let's take this sequence, okay, and we proved before that this sequence does not converge, okay, but see this sequence is bounded because they are if we consider plus 2 and minus 2, all the sequence points are between plus 2 and minus 2. That means the sequence is bounded, but this sequence is not monotonic, right? Because it interchanges between -1 and +1 all the time. So it does not have an increasing property or a decreasing property. So if it has an increasing property, then it should have this one, an plus 1 should be always greater than an. And if it is decreasing, then an should be always greater than an plus 1. For example, the 1 over n sequence. When n increases, the total value will be decreasing all the time. And here, when n increases, for example, if you take this one, this sequence, then when n increases, the total value will always be increasing, right? Now here an is equal to n, and here an is equal to 1 over n. But in this case, it does not have such a increasing property or a decreasing property. So we cannot apply the monotonic sequence theorem for this sequence, because although it is bounded, it is not monotonic. But if a certain sequence has both those properties, we can safely say that such a sequence will converge. Now, for example, if we take this one, now we already calculated the limit of this sequence as 1. So from that data itself, you can say that the sequence converges. But let's say if we don't know how to calculate this limit, okay, so then what we can do is we can use this monotonic sequence theorem to prove the convergence. Okay, now this is an important theorem, right? Because sometimes there can be sequences where it is difficult to calculate the limit, the actual limit. So in those cases, what we have to do is we should apply the monotonic sequence theorem, right? Now, in order to apply the monotonic sequence theorem for this sequence, we should check two properties. The first one is whether it is bounded or not, and the second property is whether it is monotonic or not, right? Now, for the boundedness, you can clearly see that if n is greater than or equal to 1, then an is greater than or equal to 0. And on the other way, like for the upper limit, you can see that n is always less than n plus 1. Therefore, n over n plus 1 is always less than 1. So we have the upper, we can use 1 as the upper limit, right? So now see, this is a bounded sequence, right? And also we can prove the monotonicity. So that means if we take an as n over n plus 1 and an plus 1 as, now see, if an is equal to n over n plus 1, then to calculate n plus 1, we just have to replace n with n plus 1. So it becomes n plus 1, n plus 1 plus 1, and that means n plus 1 over n plus 2. Okay. And to prove the monotonicity, as I explained before, we can use this back calculation method. Or in other words, this is the rough work that you should do. And you can start your correct real answer from this step. So you can start with this one, which is a true statement, and then you can add 2n to both sides, n squared plus 2n to both sides, and then it becomes n2, and then this is n plus 1 times n plus 1. So by cross multiplying, you can obtain this one. Okay, so that means an is greater than or equal to an plus 1. Less than or equal to an plus 1. Okay, so this is the way, if you are writing the answer for the exam, this is the one you should write. And this goes for the rough work. Okay. Right, so anyway, what we have done is we have proved that our sequence is bounded as well as increasing. So that means this is monotonic. So according to the theorem, we can safely say that the sequence converges. Now see, if you draw a picture, things will be more clear, right? Now this is the upper bound, okay, and we have a increasing sequence. Now if we consider the x-axis as the natural numbers, then we have these discrete points, okay. So each and every point we mark the function value or the sequence value, right? So now since it is increasing, when n takes larger values, the corresponding an value should be greater than or equal to the previous term. But the thing is, we cannot pass this upper bound, right? Now in our specific example, the upper bound we considered was 1, okay. So the meaning of upper bound itself says that all the sequence points are less than or equal to 1. So that means although it increases, it cannot go beyond 1, right? So definitely it should approach or asymptote with 1 in order to satisfy both these conditions, increasing condition as well as this bounded condition. So from this picture also we can say that the sequence converges to 1. But the thing is, now you should not you have to extract out the data correctly when you say, when you state these theorems, because now instead of considering 1 as the upper bound, we can even take another number greater than 1 as the upper bound, because now if the sequence points are less than or equal to 1, then definitely they are going to be less than or equal to 10, okay. But the sequence does not converge to 10, right? Because now here we have 10 and the sequence can converge to a value less than 10 also, right? Okay, so just like this number being an upper bound itself does not guarantee that the sequence will converge to this specific number, because you can take any number you need as the upper bound as long as it is greater than 1 in this case, right? So be careful, like the upper bound means it is not the it may not be the limit of the sequence all the time, right? But anyway, keep this idea in mind. Having an upper bound and an increasing sequence restrict the sequence to go beyond a certain point, but since it increases, it should possess that increasing property throughout. So the only possibility is to asymptote with a certain value, and that certain value will be considered as the limit. So from this theorem, it only says about the convergence, right? So if a sequence has these two properties, then it converges. But from this theorem only we cannot find the limit, okay? Now we know that the sequence will have a limit, but we don't have any sufficient tools to find this limit explicitly from this theorem, right? For that we will need some more mathematical techniques. And now I explained all these things for increasing sequences, but the same goes with decreasing sequences as well. Now see, if we have a decreasing sequence with a certain lower bound, then it cannot go beyond this lower bound. So the only possibility is to approach a certain value, or in other words, to asymptote with a certain value. That means to converge to a certain value. Okay, so that conclude all the required information for sequences. Now keep those theorems in mind, right? Now we have discussed few theorems. This is the one that converts the sequence to a function, and this is the squeeze theorem, and then this is the modulus relationship. Now this is only true for zeros, okay, not for any other values. If the modulus converges to 0, then the sequence will also, without the modulus, will also converge to 0, but this is not true for any other values. And we have these relationships, right? You can manipulate the sequences in whatever the way you want, right? Now see, even for this one, here C represents a constant. Okay, so now for example, if we consider C as 10, and if we consider this sequence C times an, it forms a different sequence, right? So the limit of this sequence will be equal to C times the limit of this sequence of the original sequence. Likewise, you can handle the limit of sequence in a nice way, right? Now these properties of limits are the same as you did for the properties of a limit of functions, right? Like those two are exactly the same, right? And then finally we did the monotonic sequence theorem, right? If a sequence increases and if it is bounded above, or if it decreases and bounded below, then the sequence is a converging sequence, right? Now please keep all those things in mind, so it will be very helpful when you are dealing with the other sections in our course, as well as in other different mathematics courses.